Hello, my name is Michael Berry. I am pleased to present this webinar today. The webinar is on the economics of transportable biomass conversion facilities for producing biochar, briquettes, and torrefied wood utilizing forest harvest residues. Really, more than anything else, I want to tell you a good story about the research I've done with the Waste to Wisdom project for this project. So the Waste to Wisdom project is a biomass project funded by the Department of Energy and led by Humboldt State University. It's about bringing residues, converting them into bioproducts for a marketable solution. The outline of the webinar is I'll introduce kind of the project, the question, the background, and I'll go into its context, as well as the method and applications we used for our study and their results and lessons learned. So the Waste to Wisdom project, it's a catchy name. Really, the waste we're talking about is the forest harvest residues, which are currently a business operations byproduct. They're often burned on site because it's too costly or inefficient, or there's no market for the material itself. The solution proposed by the Waste to Wisdom project is looking to convert this waste product into a valuable co-product for a marketable solution. The research focus on the Waste to Wisdom project itself is on transportable conversion facilities. Broadly, we're looking at different markets, logistics, conversion technologies, economic and life cycle analyses, as far as the whole Waste to Wisdom project. And if you've been on the line with different webinars from this project, there's been many pieces of the puzzle already explained to you. But today, we're going to focus on the research question being, what are the economic and logistic implications of transportable biomass conversion facilities? So really, the transportable aspect of the conversion facility design. So at this point, you're probably asking yourself two questions. What do we mean by forest harvest residues, and what are transportable facilities? Well, let me tell you. So forest harvest residues, as Ted Billick would say in other Waste to Wisdom webinars, are the odd sods, bits and pieces that are left over after a commercial harvest. This would include small diameter trees, non-merchantable species, tops, branches, stuff that breaks, pretty much everything that's not going to meet customer specifications and is left on site after a commercial harvest. This, of course, depends on the species, the objective, the system they're using for harvest, in particular the market. If we have a pulp market in the region or the area, then a lot of the log-like material, the small diameter trees, will be sent to a pulp mill. If not, that material will be left on site and part of the existing or the remaining residues. So for this project, we looked at two different commodity classes. The first of which being branches, kind of the branches of the trees are left on the ground. They are bulky, hard to transport, often high dirt and ash content. And then we also have, so that's one commodity class. Second commodity class would be log-like material, and this can include tops. For this project, we looked at everything 4 inches in diameter and lower as being tops. And if there was a pulp market, then pulp material, log-like material would not be on site. But if there was not a pulp market, then this material between 4 inches and 6 inches was considered pulpwood. The moral of the story here is log-like material, as you can imagine, is much easier to move off-site, transport, and it's much cleaner, so you can actually chip the material versus grinding the material at a cost savings. So there's two commodity classes that we're looking at as material left on site. So the real problem here is overall poor quality, there's high logistics costs, and there is no market for this material. Within many other studies, logistics can mean many things. In this study, we're looking at the handling, transportation, and processing costs involved. So the solution, as the Waste to Wisdom project put it, is near woods conversion. So bring the conversion facility close to life. And in so doing, we can reduce transportation costs, and we can add value to the material by making a marketable product in the conversion process itself. Now, for this project, we've considered 3 technologies or 3 products that are considered to be well suited for transportable design. These include briquettes, so residential or commercial heating fuel, torrefied wood, which is considered to be a coal substitute, and biochar, which can be a soil amendment or a filtration element. Now, other webinars in this series have gone through each one of these technologies and talked about the economics and the product itself. Here, we're kind of we're looking at this suite of technology, but also looking at the transportable aspect of design and how that would look like in the marketplace. So what is a biomass conversion facility? Well, first off, I'm going to mention BCT, and that's Biomass Conversion Technology, or in my case, a Biomass Conversion Technology facility. So a transportable facility is one that's closer to the woods. It moves throughout the landscape, allowing it to be closer to the source material. It is truck-mounted, highly modular, and able to move around and produce product, like I said, near woods. Now, as you can imagine, this is kind of by default a off-grid setup. We're primarily using diesel generators for fuel. The site layout, it depends on the size of the facility. We're looking at around 4 acres to facilitate the conversion processes. So, being closer to the woods, naturally, our advantages are to reduce transportation costs, flexible in the scale of size. This disadvantage is that you may be running at the optimal scale for your process. With off-grid energy, could be more costly. You may have downtimes, and maybe more. So, how does this fit within the broader context of knowledge? So, transportable facility design really comes at the intersection of many other forestry and biomass research and disciplines. These would include, different supply pathways, centralized facilities, the design of a facility, optimization of a broader supply chain, looking at emerging technologies, and there's also existing research related to mobile conversion facilities. So within this study and within this project, we're kind of blending this discipline within the broader context. Now, in order to evaluate transportable facilities, we had to look at a number of specific research objectives. Here, we tried to tease out the nuances of scale, mobility, biomass availability, energy and power sensitivities, logistics, product assumptions, the regional landscape to which it's in. In order to complete these objectives in this scale, we need to develop and synthesize a biomass supply chain economic model. In particular, our contributions from this work are related to facility logic, facility economics, and regional viability and sensitivity, of which I'll get into more detail now. But first, looking at the broader impact of the study and the project, we're trying to support modern efforts to sustainably use natural resources and contribute to the emerging field of biomass and bio-based products. At the end of the day, we're trying to help develop a marketplace for underutilized forest products to support local economies and produce energy independence. This is a DOE-supported project, after all. So, in order to complete this research and make these contributions, a landscape model had to be developed, incorporating a variety of methods and techniques. In particular, we had to determine what biomass was available. And after we figured out what biomass is available, how can the biomass move through the system, and what does the supply chain look like? Once we figure out what the supply chain looks like, we need to know what the costs are of the supply chain, including machine costs, facility costs, all the costs to populate this landscape model. Then once you kind of have the system outlined, you define the optimal solution, or kind of the ideal situation to which you can lower costs, and look at a case study and application. I'll now go in through the methods in a little more detail to kind of explain what we're doing and the purpose of the research. So first of all, we need to know what material is available. We looked at a 5-year time horizon to get a better handle on the movement frequency of the transportable system. And it all started with a harvest schedule. This harvest schedule was informed by markets, harvesting system, ownership class, management objectives, the landscape and the region to which we're looking at. This work was completed by the University of Washington Rural Technology Initiative that pretty much provides the raw data of which parcels will be harvested and what material will be available over the 5-year horizon. We looked at a 3-state region, Washington, Oregon, and California, and 5 subregions within there for this study. So once we have the material available, we need to know how it moves through the system. So once it's at the landing, how is it going to get to the market? And here, here's a simplified version of it, but really we can handle or process the material at the landing, then send it to the conversion facility. We can send the material from the landing to a centralized landing, process it there, then send it to a conversion facility, or we can send it right from the landing to the conversion facility, eventually going from the conversion facility to the market. So these are a sequence of pathways which really then become routes in a mathematical formulation of the problem. And here we're trying to minimize systems cost to get the best or the optimal solution to make the most value for the product. The decision variable here is the flow of material from a landing to a conversion facility using a certain route to the market. Now, as you can see, there are many costs involved with the supply chain. In order to populate these costs to run this economic optimization model, we need to first develop machine rates and specifications for equipment. This was done with the Schatz Energy Lab, Humboldt State University, and the Forest Products Laboratory. In particular, we're looking at the modularity of the technology, their throughputs, their rates, and what does the conversion technology looks like and how much does it cost, processing costs, transportation costs, market information to populate these respective costs. So in order, let me see here, okay. So in order to determine the facility, plant, supporting systems, mobilization costs, a facility costing model was also developed in tandem. So really we're looking at the machine rates, but then we're putting that into the whole systems view of what a plant would look like and operate. And this was done at Oregon State University in conjunction with the Wood and Science Engineering department over there, looking at capital costs, operating costs, mobilization of a facility as it moves through the landscape, in particular looking at 6 different facility locations. So putting it all together, so we have how material moves through, or how much material we have, how it moves through the system, what are the costs associated with it, let's optimize the system. Here is a kind of visual representation of the optimization modules when the material comes from the harvest unit and then goes to the market. So now we have a model, and we're trying to figure out, how we can apply the model and get results from it. We've split this up into two separate categories. One, kind of looking at a more localized, looking at the concept of transportable facilities. In particular, looking at a number of key considerations, including mobility frequency, scale, biomass, availability, logistics. Here we chose to look at a case study in Lakeview, Oregon, with one product, one location. And then we extended this to a regional analysis, looking at a 3-state, 3-product, 5-region, to get a better sense of the economic viability on a broader scale of this potential system design. So first off, kind of looking at the concept of transportability, Lakeview, Oregon case study. We looked at 3 different scales from the Waste to Wisdom project, from 15,000 to 50,000 bone dry ton per year. We looked at a biochar plant in particular, for minimizing the cost for that plant. In order to populate the biomass availability, we used 1,800 unique parcels that were thought to be harvested in the 5-year time horizon to provide the adequate data set. So to kind of give you an example of what this region looked like, we have some pictures here from the Fremont National Forest. On the left-hand side, you can see after a commercial harvest, what's leaving the woods are all the saw logs that are going to market. What's left behind on the right-hand side is the forest harvest residues. And you can see here in the Lakeview area, it's important to note, and that during this study, which was done about a year ago, there was not a active pulp market. As such, there's a lot of log-like material left on site, as you can see in the picture on the right. And this material can be more easily transported, cheaper to process, and there was also a fair quantity of branches left over as well. So looking at some of the key considerations, the first of which is, okay, I have a transportable facility. How often do I move it throughout the landscape? What would be optimal? And really this comes down to a trade-off of different costs, as you can imagine. If we mobilize the plant once versus 10 times, there's different mobilization costs. As we mobilize and move throughout the area, we're going to end up getting closer to the raw material and reducing transportation costs. So you can see on the left-hand side, kind of if you were just in one location, you have a small plant mobilization, you have higher transportation costs because you're not able to move to extract material more efficiently. But in this case, a sweet spot was between 2 and 4 times over a 5-year horizon. And we can see the mobilization cost becomes higher, but transportation costs become lower, and it becomes an optimal solution in this case to move between 2 and 4 times over the time horizon, which equates to around 1 to 2 years, depending on the location. Again, this is specific for Lakeview, looking at biochar within this region. Secondly, I mentioned we were looking at 3 different scale points in time. We found from the results that it is a significant, the economies of scale. So here, the economies favor a larger plant design, even though it is modular. In our case, we saw a reduction of around $30 a ton, or upwards of 20% of the supply chain, just going from a small to a larger scale modular facility. And this largely has to do with the efficiencies related to site development, supporting equipment, operational labor, electrical load, and facility housing. Thirdly, we can look at biomass characteristics. In this case, it really depends on what feedstock is available. If it's just branches out there, or if there is a lot of log-like material which we can transport more efficiently. We saw in this area, given kind of a set of predefined cases for biomass availability, that this cost seemed to fluctuate between 10 to 15% on a reasonable scale, which can contribute to the lower cost of the supply chain depending on the region. Thirdly, if you look at logistics, when I mentioned we're looking at a variety of different pathways, if we allow kind of the optimal suite of pathways to be used, so if it's more cost effective to use central landing, move at the landing, or the conversion facility, we see the optimal solution on the left, in this case around $30 a ton. But if we restrict the pathways to just look at handling at the landing, central landing, or conversion facility, you can imagine if we restrict the number of pathways, we have a suboptimal solution. In our case, we saw this suboptimal solution added around 5 to 10% on the supply chain for the overall cost. So kind of in summary, the base concept, looking at that in the Lakeview area, we can see that scale was the most important factor. Biomass availability also could contribute to supply chain costs. Logistics and the number of moves were of less importance. But overall, we could see, depending on the case, between 5 and 10% of the supply chain costs could be variable just due to these factors alone. And again, this is for a large-scale optimized biochar plant in the Lakeview area region. Now, extending the analysis, looking at the economic viability, we'll look at a 3-state, 5-region, 3-product area. So first, we're extending it to 3 products. So not just biochar as in the last example, but biochar, briquetting, and torrefied wood. I can't state enough that this research was really related to the technology employed by the Waste to Wisdom project, so it's very technology specific. In this case, our biochar facility was fairly labor intensive. The briquetting required a fair amount of drying, and the torrefied wood was highly energy intensive, and this was due to an electrically heated screw during the process. So these costs, while we're looking at these modular technologies, are highly dependent on the conversion technologies, and the results of which are contingent on those. So secondly, kind of the regional differences. We focus up into 4 different segments, the first of which being log specifications utilization, which is really just the market. Is there a pulp market or not? Secondly, energy rates. As you can imagine, the rates of diesel and electricity are higher in California than they will be in Washington and Oregon. Truck regulations in California, you cannot load a truck up to as heavy weights as you can in Oregon and Washington, and also different silvicultural and disposal costs. So really wanted to tease out what regions make the most sense for this transportable design, and how much does that vary. So in particular, looking at the regional characteristics, we can see it was highlighted in red in Oak Ridge, Oregon, and Port Angeles, Washington. There was an active pulp market, and you can see the percent tops in these cases are much lower percentage of the overall biomass than they were in other locations. This would indicate tops are higher quality, easier to transport, cleaner product. So then you can say that less tops would be essentially a disadvantage to the supply chain. So I'd like to now move the webinar here, looking at a sequence of questions that an investor might ask when trying to determine whether this is a viable system to use. The first of which is, what are the different supply chain costs? As I said before, it's highly contingent on technology involved. You see in biochar a high operational expense, in torrefied wood a high conversion expense. But overall, we see for these assumptions, the regional variation, the overall costs only vary 5 to 10%. So it's relatively minor cost variations within the supply chain. I'd also like to highlight in the bottom, kind of the shaded green area, that the logistics costs, as far as the percentage of the overall supply chain, is only on the order of around 20%, which is dwarfed in comparison to the conversion and facility costs for each of these technologies. So secondly, So that was the cost. So now, would the market bear the cost? And that really comes down to what your assumptions are for conversion and the market value. We got our market estimates from the University of Washington, and this was within the broader Waste to Wisdom project. We can see here that biochar appears to be the best, most likely candidate, largely because kind of biochar is a product that is being developed, and there's not really a set market for it just yet. So the values can range from $100 a bone-dry ton to upwards of $3,000 a ton. So we see, given our cost of around $1,000, you may be able to produce a viable product. This does not appear to be the case for briquetting and torrefied wood, given our market assumptions and our cost assumptions. So when we're talking about a transportable system, the next logical question becomes, okay, well, if we're moving around the system and we're looking at off-grid operations, we're consuming a lot of diesel, essentially. So would a change in diesel price affect profitability? Overall, our consensus was this is unlikely. It appears that diesel prices, and these graphs show a high of $4.50 per gallon for diesel and a low of $2 per gallon for diesel. And it can vary plus or minus 5%, give or take, depending on the product. So this did not seem to initiate profitability. And in particular, within the diesel price fluctuations, we see from the inset graph here, the pie chart, that most of the cost increase and decrease relate to conversion, facility, and not transportation costs, as one may expect within a transportable design. So naturally, the next question will become, well, if conversion and facility costs are high and diesel prices, and most of them are related to these conversion facilities, what if we were grid connected? So what if there was a shore power at the site? Would this enable viability, or would this save? We found in our study that the energy cost differential, or essentially the savings of energy with respect to being grid connected, was for biochar around 6–7%, torrefied wood upwards of 30%. This varied depending on the region and the state. As you can see, there's a higher incentive to go to a grid connected energy supply in Washington, where energy costs are lower than, say, in California. So what would the cost be if we had a grid-connected plant? Would this enable viability? We saw we can, reduce the cost substantially. We see overall that biochar and briquetting could now be viable. Torrefied wood is still likely too costly, even given grid connectivity. So overall, that was quite important. So to summarize our results from this project, looking at the concept, we see movement between 1 and 3 years being optimal. We see it favoring a larger scale design. We see the cost structure of the technology and conversion being much higher than logistics. We see low regional variations overall. When we incorporate diesel price sensitivity, we see a relatively low variation there, but with most of that coming from conversion and facility costs. If we were to connect that to grid availability, this can be significant, and it may be the key to initiate viability within some of these products. Overall, we looked at a 3-state, 5-region, 3-product solution. We see that likely biochar seems to be the best solution, but possibly briquetting, depending on the energy scheme and the drying configurations. But overall, we see biochar is most likely the best candidate, given its potentially high value in the marketplace, which is still evolving, its low transportation costs, and its low dependence on energy. So the lessons learned from this research and this project are namely that scale is an important consideration. We saw a much lower supply chain cost with a higher scale, even though it was modular. We saw logistics are important, but largely overshadowed by this plant and operational expenses and the technology chosen. We saw regional considerations are important, and when there's not a pulp market, this does impact the overall supply chain cost, but this is also dwarfed by technology. And technologies themselves, obviously important, but their conversion cost and the yield, so the amount of materials actually being sent to the market is extremely important. The markets themselves, they ultimately drive the viability of any system, and that price set by the market is as utmost importance. And finally, we saw that grid connectivity, or going from an off-grid scenario to a grid-tie electrical system, even in transportable design, may very well be the key to cost-effective operations. For more information regarding this project, this study in particular we've been through today and others, please, I would like to refer you to the special issue of the ASABE Journal for the Waste to Wisdom Project. This work presented today is covered in 3 different manuscripts presented within that special issue. I would like to thank Department of Energy, Humboldt State University, Torre Products Laboratory, and the University of Washington, and our key collaborators, including Hans Sapan of Humboldt State University, the PI for this project. I would normally open it up to questions, but this is a pre-recorded webinar, so if you do have questions, feel free to contact me personally with the address provided. I would also like to just thank you for attending this webinar, and if you're interested in looking at other webinars within this series, please look at the Waste to Wisdom webinar site below. And I personally want to thank you for logging in today and viewing this. Like I said, if you have any questions, please let me know, and have a great day. Thank you.